Good morning, good afternoon, everyone, and welcome to this webinar. I'm Davide, the Chief Revenue Officer here at Zinor, and today I have Dimitri, our CEO, together with me. The focus of the webinar today is about what's going on in the market. You probably saw it already that all the storage components, but not just the storage component, as well, memory and CPU, all the prices are off the roof. And the situation is carry on, started in the summer of last year, and is supposed to carry on throughout 2026 and maybe even later. So in this webinar, we will try to address this situation and see what can be done to cope with the existing situation and enable the customer to get the most out of their drives. So we will go through a few slides, and at the end of the presentation, we will be able to answer questions. So if you have any question, please write them into the chat box, and we will answer at the end. So let's look at what's going on in the market. So if you probably saw it already, or in case you try to place an order for enterprise SSD, you notice that the cost of the drive now is 2x what it used to be last year. And this situation is projected to carry on. There are news that recently came out from TrendForce showing that they are projecting high double-digit quarter-on-quarter growth. The other day, I was reading news from analysts saying that SanDisk is going to double the price in Q1. I heard that some of the vendors, they are quoting 6, sometimes 12, or even longer lead time, 12 months or even longer. We're not talking about weeks, we're talking about quarters of lead time. So it's clear that the situation is really critical, and we need to cope with this situation. So let's see what's the option, what can be done in this situation. One obvious observation, stop wasting capacity and wasting performance. And most of the time, the reason why people waste capacity and performance is because of inefficient data protection schemes. So let's see how we can reclaim capacity and performance to get the most out of the drives. So when you buy NVMe drives, you need to protect those drives because you have your most critical data on those drives. So when you deploy multiple of them, you need to do some sort of RAID or some sort of erasure coding. And you have multiple options. You can do it the old-fashioned, you can do it with a hardware RAID. But hardware RAID was not designed for NVMe drives. It goes through a PCIe bus with 16 lanes when every single NVMe drive is connected with 4 lanes. So at the best, you can get the performance of 4 drives. But in reality, you don't get the performance of the 4 drives because of the limited capability of the onboard ASIC on the hardware RAID. Then what's the other option? The other option is to use software RAID. On Linux, you have MD RAID, or you can use VROC, that used to be the Intel OEM version of MD RAID, which is now belonging to Grade. But it's basically the same software. It just comes with a dongle to enable the license. What's the issue with MD RAID? MD RAID creates a lock between the CPU core and the stripe. And this lock can become a bottleneck. If you look at what's going on when you run a RAID on MD RAID from a CPU perspective, you will see that some of the CPU core are idle, and some of them are exhausted to 100%. And that's because of this locking. And this locking leads to multiple memory copies, which waste memory, and it wastes CPU cycles. So what's the other option? The other option, you're probably familiar with one of our competitor, the company called Grade, that tells you that you need a GPU to run the RAID. We don't believe so, but I will try to explain you why not. When you add a GPU, first of all, you're giving up a PCIe slot, you're giving up 16 PCIe lanes, and you're adding latency in the communication between the CPU and the GPU. So we'll get in a second to some numbers. And ultimately, you have the option to use our RAID. And let's start looking at our mainstream product, which is Z-RAID Classic, which has been in the market since the inception of the company. It uses two fundamental technology. We use AVX technology on x86, and that allows us to do very, very fast checksum calculation. And then we combine it with our data path, which is a lockless data path, which allows us to dynamically allocate the stripe to the available CPU core. And by doing that, we can distribute the load and minimize the load per core, avoiding to do any memory copy. Indeed, we don't require any meaningful amount of memory, which, by the way, is getting extremely expensive. So that if we complain about the price increase on enterprise SSD, we should complain even more for the drastic increase of the price of the DRAM. And we basically don't use any DRAM because we don't have a cache on our RAID engine. So I presented you 4 different options. In this slide, you have a benchmark of performance, which is not done by ourselves. So what we did in this slide, we collected the input from the best number declared by all the vendors. So we collected the number from Grade on their Supreme RAID in RAID 5, running on the same server with the same drives where we run our Z-RAID Classic RAID 5 together with our partner Kioxia. And we compare it with MD RAID in RAID 10 and with Mega RAID, in this case, over just 16 drives, the same drives, but only 16, because those are the public information available from Mega RAID. And it wouldn't make any difference if you had 24 drives, because at the end of the day, you only have 16 PCIe lanes on the hardware RAID. We compare with MD RAID in RAID 10 because if we were to compare it in RAID 5, the numbers would be even lower. So we see many customers, many organizations are using RAID 10 on MD RAID just to get some performance. But as you can see in this chart, you can get some good performance in sequential read, and that's pretty much all. So when it comes to sequential write, we can get 2x the performance of MD RAID in RAID 10, and more than 10 times the performance you can get from Mega RAID. And when it comes to random, again, you see that there is a huge difference in what we can achieve versus what all the other RAID engine can achieve. Pay attention for a second to the random write. You see, I mentioned that adding a GPU adds latency, and this is very visible when you look at the random write performance for a Supreme RAID in RAID 5 against Z-RAID Classic in RAID 5. So we are 3 times faster because we don't have this extra communication layer. Okay, let's look at how this translates into savings. So if you are deploying MD RAID or VROC in RAID 10 today, you're wasting 50% of the capacity. So let's look at one real example. So if you have one server with 24, 30 terabyte NVMe drives, when you implement MD RAID in RAID 10, you get a theoretical capacity, a raw capacity of 720 terabyte, but in reality, you are only using 360 terabyte for the data. And if we compare with our Z-RAID implementation in RAID 5, we are using 23 drives for data and just 1 drive for parity in RAID 5. So the usable capacity is 690 terabyte, which is almost the entire capacity, and 2x what you would get with MD RAID in RAID 10. And if you look at the performance, you get a benefit. So you're not, it's not a compromise. You're not giving up performance. You actually improve the performance by getting 2x the capacity. But let's look at the same example from a different angle. Let's assume that you need 360 terabyte. You just need 360 terabyte usable. So today, give or take it, the cost of a 30 terabyte drives is about $5,000. And probably today it's even higher than $5,000 because the price keeps going up. But let's assume $5,000 for a 30 terabyte TLC drive. When you want to get 360 terabyte on MD RAID in RAID 5, you will need to invest $120,000 just for the drives. With us, you only need 1 parity drive and 12 data drives, and you get 360 terabyte, meaning that you just need to invest $65,000 with a net saving of $55,000, which is about 46%. And then if we compare about the implementation with a GPU with grade, we simply believe that there is not a single good reason for using a GPU to run the RAID. When you use a GPU to run the RAID, you're wasting 1 PCIe slot, you're wasting 16 PCIe lanes, you're adding 70 watt power consumption. And when you give up a PCIe slot, you are giving up the option to expose the performance through a network card to multiple clients. And that card becomes a single point of failure. So you also need to think about how to deploy multiple of those cards and waste even additional PCIe lanes and slots. And at the end of the day, you don't gain anything in terms of performance. Actually, you lose random write performance. Okay, let's look at some. So I present you some theoretical cases. Let's have a look at a real life example, how people can get more from their existing storage. So let me present you the case study that we did with the Frederick Alexander University with our partner Megware in 2024. So in 2023, the university bought 7 servers with 24 NVMe drives, 768 terabyte. And they deployed this cluster using Ceph with double replication. So at the end of the day, the usable capacity was 580 terabyte. The year later, we met with them at ISC and we discussed that they were not happy about the performance, they were not happy about the usable capacity, and they gave us a try. So they offloaded some of the servers to run a test with Z-RAID plus Lustre, and we implemented MDT in RAID 10 and OST in RAID 6. And then ultimately, they converted everything to our solution because what they saw with our solution was that they were gaining back capacity. They were gaining back 33% of the usable capacity, and they were improving the performance of the system from 3 to 4 times, 3 times in read, 4.4 times in write. So at the end of the day, same hardware, no other changes. They only change the software. They move away from Ceph. They implemented Z-RAID plus Lustre, and they managed to get this amazing improvement. And a year later, we worked with them on a different cluster. So the same university, the same partner. In this case, they had to provision storage to a much larger AI farm, the largest in Germany for universities. And we implemented Z-RAID plus Lustre in high availability. So protecting not just from drive failures, but also from possible server failures. This cluster is now part of the IO 500. If you're not familiar with the IO 500, it's an industry benchmark. Everybody can run the benchmark and then submit the results to the IO 500 committee, and they will publish a list twice a year with the ranking of the results coming from running their benchmark. We're very proud to say that this cluster is now the fastest cluster in the IO 500 when it comes to Lustre, and the third fastest overall. By looking at the IO 500, it gives us the option to do some benchmark against alternative solution. So let's have a look at one deployment which used the same hardware that we used in the ELMA deployment at Friedrich Alexander University. So in this case, it's entry number 7 in the list, which is the Leonardo exascaler DDN implementation. This implementation used the same Celestica SC6100 box that we used in the ELMA project together with Megware. And as you can see, the results of the benchmark that we achieved in the ELMA project was 838.99 against 648.96. So quite a good improvement in the performance. But then if we look at the hardware that was used by DDN, they used 29 of those boxes. So if we take the score and divide it by the number of boxes, and we only use 10 of those boxes, you see 4 times better performance per server. And then if we look at the amount of NVMe drives used, we use 1/3 of the NVMe drives. So the performance per drive calculated using the IO 500 benchmark is almost 4x, 3.7 times better with our solution. That's all about we do data protection in the most efficient way. Okay, so with this, let's look at other ways to optimize the cost of deploying storage. So saving on the data protection is one thing, but there are other things that we can bring to the equation. One of these is to minimize CPU consumption. CPU price is also going up, and we need to be very mindful on the way we use the CPU. The other option is to use NVMe drives not just for one client, but for multiple purposes. And if we're able to provision NVMe over Fabric, we can get the most out of those drives. And then the third things we can look at is how can we offload completely the CPU and run the storage from Bluefield. If you pay attention to what Jensen, NVIDIA CEO, said at the recent CES event, he put a lot of effort in offloading the CPU to run the storage, and with that, being able to reduce the dependency from expensive DRAM and HBM. So let's look, before we look at those cases, let me introduce our new product, or actually it's not really new. It's over 1 year that we introduced Z-RAID Opus. And Z-RAID Opus is again a RAID engine, but it's more than just a RAID engine, because we support also NVMe over Fabric initiator and target. The big difference between Z8 Opus and Z8 Classic is the fact that with Opus, we operate in user space. So we started from the SPDK libraries and improved those libraries. And by working in user space, we operate through polled mode. So we don't use interrupts. So by doing this, we are very much less dependent on CPU cycles. We can get much more from every single CPU core. And we will show you in the next couple of slides. And again, we use our calculation libraries, and we can operate from x86 using AVX2, but we can also operate from DPU or any ARM-based CPU using the vector registers within ARM. Okay, with this, let me hand it over to Dimitri, who will give you some more information about those additional cost optimization.
Thank you, Davide. Hi, everybody. Before we start, I urge everybody to ask the questions, to make a comments in the chat. I see 2 good questions, 1 great comment. So I hope that when I will finish, we will have much more of them in our chat. So related to the CPU consumption, why it's important? Because you need your CPU not only for storage, but as well you need your CPU for the applications. And what we managed to achieve, it's really great CPU utilization, which we demonstrated in our joint case study and research with Intel. We did this time research related to the modern Xeon 6 for E cores and P cores. And for both, even for energy effective E cores, we can demonstrate that just from 1 CPU core, we can get in sequential read in about 100 gigabytes per second. In sequential write, 16 gigabytes per second. 1 million IOPS for random read and 0.3 in random write. And it's just from 1 CPU cores, and it could be scaled linearly. What means in practice that just for data protection, you need typically not more than 8 cores in the modern infrastructures. All other cores you can devote to your application workload. So the next point, what is very important now, it's not only to provide data protection and to provide effective use of your local NVMe drives. As well, there are a lot of use cases which are called dark flash, when you have a lot of NVMe across your network, across your servers, and the right task is to deliver NVMe to the right client in right time. And exactly for this, we as well developed our Z8 Opus, which was introduced by Davide. So what I would like just briefly demonstrate is that when you use our Z8 Opus over the network, you can have the same performance as you can get locally, and all your performance is just limited by the network capacity. So this case, we have a very simple experiment which we did with our friends from Supermicro. So this case, we use 1 server as target for our RAID device, and the second server was the client. And what we can demonstrate then, when we use just 1 CPU core for our data protection for sequential read, we can fully utilize the network of 400 gigabit per second. And when we use just 8 cores for sequential write, you can utilize the same network just out of 8 cores. And you can get this performance not locally, but over the network, and you can expose your protected block device exactly to the client, which is most needed, this protected block device this time. So what would be this random write? In random write, with the same installation, we can demonstrate theoretical maximum for RAID 6, taking into account RAID penalty, which is 33% of overall drive performance, which could be possible to get out of this case. What even more important, that it's not only about throughput and IOPS, it's as well about latency. And in case if you use our Z-Rate Opus, then this case you can get latency which is significantly smaller than all the latency you can get out of any kernel space applications. What is demonstrated by two curves at the graph. If you could see at the curve which is green, you could see the latency with Z-Rate Opus and a server, and as well initiator based on user space software. In case if you use kernel space initiator, then you see absolutely different latency, which is in this graph by the blue curve. Okay, and it's not the final of the overall story, because using our Z-Rate Opus, you could offload all the data protection on your GPU. It's even important in many security aspects of your application infrastructure. When you default GPU for data protection, and it's isolated from your application layer, which is working on the host side. We did a joint research with NVIDIA. In this case, it was NVIDIA lab out of China. We did this research with them in about 1 year ago, and it was presented at the last GTC, the March of the last year. So this case, we use network attached drive. We use BlueField 3 on the host side. We run our engine on BlueField 3 on the host, and we expose our RAID for the application on the host side. And we compare results that we get with two different installations. In two different installations, we used data protection on a host side, which was MD-RAID, and our implementation of Z-Rate Classic. So what we can demonstrate for sequential write in BlueField. You can see that we can demonstrate much more better performance than MD-RAID. The performance is comparable with Z-Rate Classic, but if you look on the CPU consumption, for sure, when you use BlueField, you almost has no consumption of the CPU on the host side. But what is even more important than reduction of the CPU consumption is a security aspect. That this case, you isolate your data protection out of your application layer, and it's exactly the case which was discussed at CEC this year and was presented by Jensen several days ago. Related to the random read, with BlueField 3, we have some limitations based on software stack implementation for BlueField 3. And this case, we can get only 15 gigabytes per second. Only, it's not only, it's as well not bad numbers out of 5 drives. We can get 15 gigabytes per second on BlueField 3, and this limitation was basically relates with BlueField 3 software stack, and we are sure that in our upcoming research, which we are doing with NVIDIA on Bluefield 4, it would be totally different numbers. So again, what this offload is demonstrated, that you can offload your data protection on your DPU. You can as well expose this protected device locally to the host, or you can expose this protected device over NVMe over Fabric, thanks to our own implementation of NVMe over Fabric in Z-Rate Opus. And still you get very good performance for all your workloads, and it's evenly true for training and for the inference. Okay, I think that's it related to our presentation with Davide, and now it's the right time to go to the questions.
Yeah, okay, let's do it. So let me pull the question, and then we see how to answer them. So the first question is from Grigory. With a RAID 5, there is only one disk spare. What would be the recommended Z-Rate Classic? The answer is it depends. So most of the time, customer deploy RAID 6, RAID 5 or RAID 6. When you have 24 drives, it depends. If you have a dual CPU system, then you can deploy nested RAID 50, RAID 60, or you can isolate the RAID, create two independent RAID groups between each NUMA node. Our software support any level of RAID. We support M+M. You can have any number of parity drive up to 32 over 64 drives in total in a single RAID, and unlimited number of RAID. There is not a simple answer to your question. It really depends on the application, on the RAID geometry, on many other aspects. But the good news is that we support all RAID levels. Then let's go to the next question. Comparing Ceph with Lustre is not very fair for Ceph. I agree, but that's the reality of what the customer did. So the customer was running Ceph, and we convinced them that well, actually they were already convinced it was not a good idea, but they've been running for over 1 year with Ceph. And then when they tried out Z-Rate with Lustre, they immediately took the decision to move over. Okay, then next question. So when we compare with DDN Exascaler versus Z-Rate with Lustre, wouldn't DDN have higher availability score? Not really, because for metadata we use RAID 10. But the way we did it, and it's all documented in our case study with Frederick Alexander University, it's available on our website. You will see that in the architecture we're taking, for every server, we're using 4 drives for metadata, and those 4 drives are in RAID 10. And then for the OST, for the data, we have a more efficient RAID 6. If we look at DDN, they use D-cluster RAID on NVMe, so that doesn't give any additional reliability compared to what we did. Following question. How you compare a RAID 1 versus a RAID 5? Altogether is different use case. 23 plus 1 as a risk of data, and if both disk phase, it will be data loss. So how do you justify? Yeah, that's a very fair point. We're not suggesting customer to implement 23 plus 1. As I said, it depends by the application and many other factors as well. But what we see from customers is that many times they implement MD RAID in RAID 10, not because of the reliability, but just because they are looking for getting extra performance. And the message that we wanted to convey with our benchmark was not to move to just one single drive over 24 drives for data protection. The message is that if you need performance, you don't need to give up that much capacity. We can get much higher performance without giving up capacity. Okay, then the following question, I'll give it to you, Dimitri. So in your example, RAID 6 with 6 NVMe drives, you get only 1 million IOPS at 4K random reads. Bandwidth of 100 gigabyte per second seems okay, but the IOPS seems low.
Yeah, okay, thanks, David. Actually, it was example with 8 drives, not 6, and in theory, from all the drives, you can get 3 million IOPS by the drive specification. But when you combine them on RAID 6, then theoretical maximum from RAID 6 device on random writes, it's 1 million IOPS due to read modify writes, which you do for every small IO operation, because you need to, when you write data, you need to as well recalculate and write to parities, and as well you need to read data to write such parities. So out of theoretically possible 3 million IOPS, we get 1 million IOPS, which is the theoretical limit. So it's not related to the random read. Related to the random read, you're absolutely right that all the performance scales linearly related to the drive specification, what we as well demonstrate at the slide.
Yeah, so the 1 million is one single CPU core. As we add more.
No, it's not about here in this example. It was not about one single CPU cores. It was about 8 CPU cores, and this example was about writes. But if we are speaking about reads, then David, you're absolutely right that it's 1 million IOPS for random reads just from one CPU core. Exactly.
Yeah. Okay, so let's move on. Then let me see what's the following question. Yeah, to follow up on this topic, still from Joshua, is he has a question about bandwidth. So he's expecting. Okay, so I see the point. So he say 4 + 2, we should get 60 gigabyte, not 100 gigabyte. But actually, we had 8 drives, not 6 drives. That's why. We get to the 100.
Yeah, and in case of read, you can read all the drives. It's because you have split parity between all the drives.
Okay, then let me make sure I'm not missing.
I think we missed Sergey's question.
Yeah, Sergey question. Do you have an idea why performance on 2 and 4 cores is almost the same?
It's let me come back to the slide where we did it. 1 second.
Yeah, okay.
It's not this one. But it was 2 and 4. And why it's the same? I see that it's not the same out of 2 cores and 4 cores. Maybe I miss the question, but okay.
It's not this slide. I think it's the previous one.
It's as well not the same.
Yeah, again, it's not the same, and even the previous one. Okay, this one, 2 and 4.
2 and 4. Okay, it's yeah. It means that here it could be scaled linearly because even with 2 cores, we have in about 2/3 of the overall possible performance. So no chance to scale linearly this case because we consume all the drive specification metrics.
Okay. Then there is a question from Mohammed. Why Z-RAID should be faster in one node to parity like RAID 6 compared to ZFS? You want to answer this one, Dimitri?
Yeah, okay. Yeah. So related to the ZFS, ZFS is not great in all the random operations. So for every workload where you have random, and at the present moment it's almost all workload related to the AI, it's a problem that you always have with all your ZFS installations. In case if you have only sequential workloads, yeah, you're right that in some cases you could as well use ZFS, but as well you would be limited on sequential write performance, even with the modern ZFS releases. I see the comment as well from Joshua that we can get 2.8 million IOPS, and I already answered about read modify writes, I think, on this comment. That,
yeah. Yeah, I don't see any other questions. So, okay. Yeah, I think we answered all the questions. I see Joshua is still typing, so let's give him another 1 minute to be able to answer his question. Okay, maybe it would be good to get a performance versus dollars comparison against a GPU-based RAID solution. Okay. Yeah, we can do that. You know, we as a company, we are not very keen to talk too much about our competitor. We can do that. We know we have a very, very strong argument. And as I said earlier, in all honesty, I don't see any single reason why you should use a GPU to run the RAID, including the fact that you need to pay for the GPU. So if you want to look at a performance per dollars, it will be drastically in our favor because we don't need to pay for the GPU. So we are purely software. That also a software implementation which requires a dedicated hardware.
Yeah, and as well, it's all about network capacity today. Yeah, and in case if you use for high availability more than one GPU assisted RAID, then you as well squeeze your network capacity not by not by one network card, but as well by two network cards. So it's very important for all type of workloads today.
Yeah, and Joshua has a point saying that if they use the GPU, they use less CPU. Theoretically, yes. In reality, no. They use as much as CPU as we use, and I welcome you to test it because we had the chance to test it, and we had a customer who tested it and showed us that we actually use less CPU than what they do on top of using the GPU. Yeah, and Augustin also has a point, GPU are less reliable. Yes, you probably need to deploy 2 of those cards if you really want to be protected. Okay. Okay, so yeah, I think we are at the end of the time that we planned for this webinar. You have our contacts there at the beginning of on the first slide, so you can if you have further questions, don't hesitate, just send a message to myself or Dimitri or both of us, and we would be more than happy to answer your question. And again, it's software, so if you want to test it, don't trust us, trust your data. So we can provide you a trial license, and you can verify yourselves if it brings value to your application. Thanks again. Thanks for attending, and have a good day.
Thanks so much, everybody. Bye.